Hello everyone, welcome on this e-learning platform of X Institute of Physics. In this video we will talk about electric potential due to an electric dipole. In the previous videos you have understood or learned what is an electric dipole is and what is the electric field due to an electric dipole is. In this we will focus on electric potential due to an electric dipole. So let's draw an electric dipole. So assuming that there is an electric dipole existing in this manner, so that's the electric dipole. And what the meaning of this electric dipole is, you need to understand, or you need to remember that this plus, there is going to be a plus charge located, which is Q. At this tail point there is going to be a minus charge, that is minus Q, and the separation between these 2 points is D. So this arrangement is electric dipole, and its electric dipole moment P is Q into D. Now this electric potential can be found out at any point on this space. So we will start with the some important points. So first point is on the axis, just like we did for electric field. So on the axis of dipole. So let's consider a point on the axis of dipole, and for that sake let's first draw axial line. So axial line is going to be some sort of this, and on this line there is a point of interest. Let's say this point of interest is point A, which is at a distance from this dipole. We know the distances are measured from the center location, so that's the distance is, let's say, R, and we are interested in finding the potential at point A because of these 2 point charges. We know one potential will be because of point charge plus Q, another will be because of point charge minus Q. So we can say the total potential at point A is going to be potential coming because of positive charge plus potential coming because of negative charge. And because of a point charge, what the potential at any point is, we know the formula Q upon the distance. So first that means because of positive charge is going to be K into Q, which is the charge Q, divided by distance from the positive charge of this point A, which is going to be R minus D by 2. So we will write it as R minus D by 2. And then potential because of negative charge is going to be minus, so I can place a minus, is going to be K into charge Q. Minus of this Q charge has come outside, and the distance of this point A from this minus Q charge is going to be R plus this half extra, which is D by 2. So that means R plus D by 2. We can simplify this to get our simplified expression. So V is going to be equal to, we can take this KQ outside, and within the bracket they will have cross multiplication, so it's going to be R plus D by 2 in one bracket minus R minus D by 2 in another bracket, divided by product of these denominators. So it's going to be like A minus B, A plus B. I can directly write it as A square, that is R square, minus B square, which is D by 2 whole square. Now to carry forward this calculation, you will find this is going to be equal to KQ, which is a constant outside. Within the bracket you will find this minus sign expansion will lead to minus R plus D by 2. Minus R and plus R will get cancelled out. D by 2 plus D by 2 will become D. So this simplifies to D, divided by downside. We know here R is going to be larger number, that means D is going to be smaller number, and D is very small as compared to R. So we can ignore this part of the expression. So R square is going to be leading to D by 2. So this D by 2 can be neglected. That means it can be approximately assumed to be 0 in comparison with R square. So this will lead to simply R square downside. Now we can say from here very easily that this Q and D can be replaced by P. So potential on the axial position comes out to be K P divided by r square. So this becomes a formula to be remembered for potential on the axial position due to an electric dipole. Now once we have found out the potential on the axial position, now we will talk about the potential on the perpendicular bisector. So next point that we are going to deal with is potential. Let's say we can discuss here second point, and the potential we are interested on the perpendicular bisector. Perpendicular bisector. So let's draw first a dipole, then draw a perpendicular bisector. So let's say a dipole is existing over here. So that's a dipole. And let's draw a perpendicular bisector. That means a line which runs perpendicular to this and 90 and passing through the center point. So that's the line I'm drawing over here. Let's shift a bit here so that it is at the mid location. On this line we are interested, we are considering a point. Let's consider a point on which we are interested to find the potential. So let's say that point is A, and that point has a distance r from the dipole. So this distance is r, and this is a dipole. Dipole means this is a plus q charge and there is a minus q charge, and since it's a bisector, so it's going to be d by 2 distances. Now what we need to do to find the potential, we need to measure this distance. So if we measure this distance for first and this distance for another, then you'll find both the distances are going to be equal. So potential at point A, because of positive charge and because of negative charge, can be calculated. Let's call this number as a z, distance as a z. So this distance also will be equal to z. Can we say the total potential at point A is going to be because of positive charge plus because of negative charge? Because of positive charge, the potential will be kq upon z. Z can be written in terms of r and d. We will write it later on. Because of negative charge is going to be negative, so it's going to be kq upon z. If we combine the two together, it will be 0. That means at point A, the potential turn out to be 0 on the this perpendicular bisector. So this is another result to be remembered, that the potential on the this perpendicular bisector of this dipole is 0, and that means on the equatorial position it is 0, on axial position it is kp upon r square. Right, so using these two expressions or results, we can find out the electric potential at any point due to an electric dipole. So let's calculate that as well. So here we will find the electric potential due to an electric dipole at any general point. So let's start with drawing a dipole. So let's say this is electric dipole P, which is just 1 minute, let me redraw it. Electric dipole P is existing like this, which will be combination of plus charge and minus charge. So I'm drawing P over here, so that's electric dipole, and we are interested to find out the electric potential at any general point. So reference has to be from the center, and this is the general point A, let's say, and this A point will have its address that will be measured by distance r. That means r theta system, and theta has to be measured conventionally from positive direction in anti-clockwise sense. So that's going to be theta. So this will be the location of A. Now we need to find the potential at point A because of this dipole. So we can follow the same rule. Because of this vector nature of the dipole, we can make the two component of this dipole, and one component will be pointing in the direction of radial. So one component will be in this direction, radial direction, and another component will be perpendicular to this radial direction. So that will be along the tangential direction, we can call it. And if this is a P, this is a theta, so we know this component will be P cos theta, and that component perpendicular to that radial direction is going to be P sin theta. Now the potential at point A because of P will be same as because of its components. because components also represent the same vector. So because of the, let's say, p cos theta component, because of this p cos theta component, this point A will be on the axial position. Because of p sin theta component, this point will be on the perpendicular bisector. We know on the axial position the dipole is on the axial position of the dipole the potential is kp upon r square, and on the perpendicular bisector is 0. So that means if combine the two, so we can say the potential at point A is going to be equal to, because of p cos theta, it will be k into dipole, which is p cos theta divided by r square, plus because of p sin theta component, because of p sin theta component, this point will be on the perpendicular bisector, and we know because of at the point perpendicular bisector its value is 0. So this will give us the result, which is important result. That means potential at any point due to an electric dipole is k p cos theta divided by r square, where the term has their own meaning, the meaning that we have understood till now. So let me say this potential is at point A, which is at r theta from the dipole. K is the 1 upon 4 pi epsilon naught, 9 into 10 raised to power 9, we know. P is electric dipole, that will be given to us. Theta is the angle that it makes, and r is the distance from the dipole. So this formula will let us know the dipole, this electric potential at any point because of that dipole. Now if we substitute theta equal to 0, we will find this is going to be axial position, answer will be kp upon r square. If we place theta equal to 90 degrees, it is going to be equatorial, that is perpendicular bisector, potential will become 0. So this important result has to be understood and remembered. So in this video we have understood the electric potential because of an electric dipole at different locations. So this formula will talk about this entire result. Thank you for watching. Have a good time.